Back to our segment on complex integration. So I want to remind you of the basic notions of integration that we've talked about recently. We talked about the real integral, which is equal to a limit of as a partition norm goes to 0 of a Riemann sum that looks like this. We've talked about the path integral, which is similar, except we take f of gamma of the sample point tau and gamma of ti minus gamma of ti minus 1. This is, in a way, a direct analog of this from the perspective of moving in the complex plane from the point gamma of A to the point gamma of B, which are complex numbers. Then we have the Riemann-Stieltjes integral, which is a direct generalization of this, where we take any function instead of a function composed with gamma here, and that gives us this form. Now, these are all very tightly related, but they all have their own notations. So notice these three notations are very distinct. These have gammas. This is d gamma. This is dz. But they are related to one another. The path integral is a kind of Riemann-Stieltjes integral. It's the Riemann-Stieltjes integral d gamma of the function f composed with gamma here. And the real integral can be regarded as a path integral in one way, but it can also be regarded as a Riemann-Stieltjes integral in another way. So as a path integral, it is the path integral using the identity function gamma, which maps from AB to AB, which notice is in a subset of the complex plane. So if we use gamma to be the identity, then it goes away here, here, and here, and we end up with this formula, and it's then a formula for the integral from A to B of f of z of f of x dx. So the ordinary Riemann integral is a path integral if we use the identity path. It is also a Riemann-Stieltjes integral, again, if we use the identity path. These gammas go away. So the Riemann-Stieltjes integral is really the most general integral that we will be talking about in this course. And in order to really understand it well, we need to understand this limit as the norm of the partition goes to 0. We need to develop a little bit of theory for that. We also, as we're looking ahead, we need to think about what kinds of gammas are we willing to accept here. In this definition of the Riemann-Stieltjes integral, I've given this thing and I've simply said gamma is a function from AB to C, and f is a function from AB to C. I'm not even assuming that they're continuous functions. They could be just relatively arbitrary, just completely arbitrary functions. Now, if gamma and f don't obey any reasonable properties here, then when we try to calculate this limit, we'll expect this limit won't exist. So we don't need to account for this in the definition, but we do need to find criteria for gamma and criteria for f that will guarantee us that when we actually calculate this limit, that it does equal something. So as we're moving ahead, what we really need to do is we need to understand under what conditions on gamma and f can we be assured that this integral actually exists, that this limit is defined. So that's what we need to do moving ahead. Now, before we get to that, we need to look closely at this behavior of this limiting thing. And we need to study limits as partitions get finer and finer. So the first thing that I would like to shed some light on is that we're really talking about general functions from partition space to the complex numbers. So let's let phi be a function from all partitions of AB to the complex numbers. And then it's really in this context that we should be considering the limit as the partition norm goes to 0. So if so then let me say we have defined the limit as the partition norm goes to 0 in this relatively arbitrary context, any function of a partition to be the L such that for every positive epsilon, there exists a delta greater than 0, such that for every partition, let's call that capital P, for every partition capital P, if the norm of that partition is less than delta, then phi of P is very close to L. So this is our definition of this thing. Now, this thing doesn't yet take into account some important relationships between partitions. And in particular, I want to talk about the relationship of refinement, which is a relationship that partitions can enjoy with respect to each other. So if P and Q are partitions of AB, And this is possibly tagged partitions. So basically what I mean here is maybe the partitions are just partitions in the sense that they specify points t0, t1, t2, etc. Maybe they are tagged partitions in the sense that they also specify sample points tau. It doesn't matter for this definition. So we say Q refines P, and we write P curly less than Q. And what does this mean? This means if the endpoints Ti in P are a subset of the endpoints of Q. So it's convenient to have a picture. So it's convenient to have a marker that's effective. So let's draw a representation of AB. And then on this same representation, this could be T1, this could be T2, this could be T3, and then this could be T4. So that would make this T0, of course. So there, that could represent the partition P, right? So P is going to be consisting of these values, T1, T0, 1, 2, 3, and 4. Now Q will be its own situation. Q will define some endpoints Si, and if the Ti's are among the Si's, then Q is finer. So this will be S0. S1 might be here, and then S2 could be this one. S3 could be here. S4 could be there, and maybe S5 is here, and S6 is there, but S7 is here, and then finally maybe this is S10. So this would be a situation in which the partition Q is finer than, refines, the partition P. So when we use the language refines, basically think of it as it cuts it up into smaller pieces, right? The partition divides the interval into pieces. If Q cuts it up into smaller pieces, but that's not simply saying that the norm of Q is smaller than that of P. It's not simply saying that the parts in Q are smaller than the parts of P. It means that it cuts it further, right? All of the Ti's are among the Si's, and then there are possibly more Si's. So that's what it means for a partition to refine another partition. And as we move along towards norm 0, it seems like the finer the partition, the closer it is to 0. And of course that's true. So if P is refined by Q, then the norm of P is going to be greater than or equal to the norm of Q. So Q is doing a better job refining the partition, and that's why we define it to be the greater here. It's sort of doing more to refine. Now, sometimes we have to deal with functions phi, which have a predictable relationship to refinements. And so since we have now an inequality relationship, an ordering relationship among the partitions, then we can talk about whether the function phi is going to be increasing or decreasing. That is, so long as it maps to R. So let's give this a definition and see where we're going with this. So if phi maps partitions, and in this conversation there are always partitions of the same interval. If phi maps partitions to the real line, it has to be the reals because I'm going to be using the order relationship of the reals. So we call phi increasing, and this is weakly increasing, not strictly increasing. We call phi increasing if whenever Q refines P, then phi of Q is greater than or equal to phi of P. So if we have an order structure on the domain and an order structure on the range of the function phi, then we can talk about whether phi is increasing. And this is what it means for phi to be increasing. Now, if an increasing function has a limit in this sense, then that limit will be its supremum. And that will be convenient for us to know later. So that's what we're going to prove right now. And if this is starting to sound like limits of sequences, that's good, right? This should sound all like prior work having to do with sequences. The role of the sequence is being played by phi, and the partition in this analogy is actually playing the role of the natural number. The partitions living in the domain of phi should be thought of as analogous to the domain of a sequence, which would be the natural number indices there. So the partitions are actually playing the role of the indices of the sequence. And then phi is playing the role of the sequence itself. And so if you have an inequality among the indices, then you get the same inequality in the terms of the sequence. Phi of p is playing the role of the term of the sequence. And we have easy statements for sequences that say things like, if a sequence is monotone increasing and has a limit, then that limit is its supremum, right? We also have other sequences like the monotone convergence theorem that says if it's monotone and also bounded, then it must have a limit. So a lot of these sequence theorems have translations for functions whose domain is the set of partitions. We only need a few of them, so we're not going to go really, really far into this. But one thing that we do need is we need to know that the limit of these things, if we have an increasing function, then the limit and the supremum are going to be the same thing. So let's state that precisely here. So theorem. So if phi, and I'm going to, well, it's the same phi, maps from partitions to reals, if that is increasing, and if the limit of phi of p, and of course that's in the only sense we have, the limit as the partition norm approaches 0, if the limit of phi of p is equal to L, then we get furthermore that the supremum of phi of p is equal to L. Do I need to give a special definition of the supremum for this crazy case where we have partitions? No, actually, that is the regular supremum. This is the supremum of, so it's the supremum over all p here, right? But as p varies, phi of p varies within the reals. And so this is just basically a subset of the reals. And we're taking the supremum of that subset of the reals. So I don't need a special definition. This is just the supremum of the real numbers, which are the values of phi at the various inputs of phi. Since they are all real numbers, the supremum is already defined. So basically, if this new fancy limit is equal to L, then it's equal to the same supremum of that. But only if the thing is increasing, of course. So let's give a proof of this. It's not especially hard. In fact, it's very similar to the same proof that you would give for sequences. If you write down a proof of this that would work where phi is a sequence and it's an increasing sequence, then that proof basically goes through without any extra effort. And if you're thinking, well, then this is part of some even more general situation, well, then you're right, it is. But we're not going to go too crazy with the generalizations here. So, so let's prove this theorem. So we're going to assume, of course, that the limit as the partition norm goes to 0 of phi of p is equal to L. And now I'm trying to show that the supremum of all of the phi of p's that could possibly exist, all of the partitions, is equal to L. So what I'm going to do is I'm going to show that phi of p for any p is always less than L. Now I want to change the notation here, so I want Q to be a partition. So let Q be a partition. And what we're going to do is we're going to show that phi of Q is always less than or equal to L. We're going to let epsilon be greater than 0. And we're going to choose a refinement. Hold on. First, we're going to choose a delta. So we're going to choose delta for epsilon in the definition of the limit. What does this really mean? It means I chose my epsilon to be greater than L. Apparently, I don't know how to do analysis. Epsilon is always going to be done greater than 0. So what does this mean to choose delta for epsilon in the definition of the limit? It means that, well, we're going to choose a delta so that it is true that whenever p is finer than delta, whenever the norm is less than delta, then the distance between phi of p and L is less than epsilon. Okay? So then we're going to choose a partition R refining Q. So we're going to choose a partition R so that Q is refined by R, and the norm of the partition R is going to be less than this delta. Is that always possible? Well, sure. Q might not have a norm less than delta, but you can just add subdivisions, add endpoints until the norm is less than delta, right? So keeping the ones in Q so that you can get this thing less than or equal, so refined by R. So, so then we choose a partition R so that this is true. And then, well, phi is increasing, right? So phi of Q is going to be, so because Q is refined by R, phi is increasing, that's going to be less than or equal to phi of R. But that is strictly less than L plus epsilon. Why? Because phi of R minus L absolute is going to be less than epsilon. So phi of R is going to be less than epsilon distance from L. And so, so that tells us that phi of Q is less than L plus epsilon. But now I chose Q before epsilon, right? So Q was chosen to be an arbitrary partition, then epsilon was chosen next. And that means that this equation is true for all epsilon. And that means that phi of Q is actually strictly less than L plus epsilon for every epsilon, so it's less than or equal to L. And that Q was arbitrary, and so we get for all Q. And so basically this is telling us that this supremum is a supremum of a set, but every element in that set is going to be less than or equal to L. So what do we prove here? Thus we show that the supremum of phi of Q is less than or equal to L. This doesn't show that it's equal to L, but it shows that it's less than or equal to L. Now, so because the limit as the partition norm goes to 0 of phi of p equals L, phi of p can be made arbitrarily close to L by the definition of the limit again. And so what does that mean? That means that the supremum of all the values phi of p is at least L. And then, of course, you put these two together, and you get the supremum of all the values of phi of p over all the partitions is equal to L, which is what we wanted to show. So that's the conclusion there. So this demonstrates that, you know, functions on partitions behave a lot like functions on integers behave, a lot like sequences behave. If they are increasing functions in the appropriate sense, and if they have a limit, then that limit is the supremum. And that's pretty convenient to know. Now, I wonder if there are any other interesting features of partitions, functions on partitions that behave analogously to functions on integers, sequences. Well, in fact, yeah, there are. There's a Cauchy criterion, and it's going to be really handy. So let's state it carefully first, and then we're going to prove eventually that the Cauchy criterion is equivalent to conversions. So I'm going to try to make it seem natural how we define the Cauchy criterion for these kinds of functions. But of course, they're not sequences, so we do have to be careful. So at this point, so when we talk about increasing, we need the codomain of these functions to be an ordered space. When we talk about the Cauchy criterion, we don't need that at all. We just need it to be any metric space. So this is definition. So let's let phi map the set of partitions. And again, it's always partitions of the same interval. So let's say partitions of AB to X, where X is a metric space. Now, here I'm not assuming that X is even a complete metric space, but when I prove theorems about Cauchy sequences, I will have to do that. So X is a metric space. So we say phi is Cauchy if. So phi is analogous to a sequence, and this is going to be analogous to a Cauchy criterion for sequences. Let's remind ourselves what the Cauchy criterion for sequences is briefly. So let's let an be in, say, a metric space X. This has a different notation from phi of p, but it's basically the same idea. So let's let an be there. So we say an is Cauchy if, and how does that work? So for every epsilon greater than 0, there exists a cap n. And then for every m and n in the naturals, if m and n, well, if m exceeds n, and also n exceeds n, then the distance between an and am is less than epsilon. So the Cauchy criterion for sequences asserts that the terms of the sequence are close to each other, at least they are eventually close to each other. So there is some eventuality cap n, so that for any two terms beyond that position, then the difference between those two terms is small. And I see that here that I've made a mistake here. So if I'm putting this in a general metric space, then I need to use a general notion of distance, not this absolute difference. So if I'm putting these in a general metric space, then I need this distance, this general distance for the metric space. But if the metric space was R or Q, then I could simply write the distance as the absolute difference. And there are other cases when I could, but you get the idea. All right. So the point here is, how do we take this definition of Cauchy convergence, of Cauchy property, which applies to sequences, and give something sensible and useful and analogous, which applies to functions on the space of all partitions? Well, let's copy everything that we can. Without thinking, we can copy this. For every epsilon greater than 0. That's as far as we can get without thinking. Now, we would like to say there is some eventuality here. Now, in the sequence case, the eventuality beyond which things work is the cap n, and then we consider any sequences beyond that point. For partitions, they are, think of them as gradually getting finer and finer and finer, right? We're talking about the limit as the norm approaches 0. So the eventuality for partitions would be that a certain location, so that they have reached a certain level of refinement. So it would be a delta here. So the analog of this, there exists a cap n, is really, there exists now, again, a delta. And notice here, so far, so good. So far, this does not differ from the definition of a limit, right? For every epsilon, there exists a delta. Now, here, this is about the relationship between two partitions. We introduce this is about the relationship between two sequence terms. We introduce the indices, and we've talked about the indices are really analogous to the partitions themselves. So here, let's introduce two partitions. And basically, we're going to say these partitions are close to each other. When we apply phi to these partitions, we get something close. So for every p and for every q, now we need to say that, you know, they surpass the criterion that's being imposed here, right? So what does that mean? That means that the norm of p should be less than delta, and the norm of q should be less than delta. And so we should say that if the norm of p is less than delta, and the norm of q is less than delta, well, I'm going to leave a space here. So, well, actually, I'm going to put implies here, but I'm going to add something. So if both of these conditions hold, then what's analogous to stating this? Again, we can say the distance between, now, not the distance between p and q, which wouldn't make any sense. The distance between phi of p and phi of q. So that's phi of p, and that's phi of q. And here, I'm using general distance because I'm in a general metric space. But whenever we apply this in practice, we're going to use absolute difference or modulus of difference between these things. So this distance is going to be less than epsilon. Well, so that's not too bad. But in a way, that misses the point of the Cauchy criterion. There is a secret and hidden condition here that we didn't have to say for sequences that really figures in an important way for partitions. And so we need to include something else. There's something funny about sequences. When you deal with sequences, the indices are natural numbers. And the natural numbers are always comparable, right? Index 7 and index 9, you can always say this one is farther on in the sequence, this one is less. Whenever you have any m and any n, then m and n themselves are comparable. And so that's nice because that means the index set for a sequence is a totally ordered set. Well, partitions of an interval, that's not a totally ordered set. It's partially ordered by the refinement relationship, but it's not totally ordered. And here, we never had to say what happens when m and n are just not related by the ordering condition at all, right? It's safe to assume in the sequence definition that the ordering relationship at least applies to m and n. One of them is greater than or equal to the other one. Here, it's not safe to assume that, and we actually want that as a built-in hypothesis for the Cauchy criterion. Why? Because it makes the Cauchy criterion easier to prove. It makes the theorem that Cauchy criterion applies convergence harder to prove, but it makes the Cauchy criterion itself easier to prove if we pile in more into this definition. So let me fill that in. So basically what we want to do here is we want to say, and they are related by refinement. So basically, we're not asserting that any two partitions have phi of one and phi of the other are close. We're not asserting that. We're asserting that any two partitions which actually have a refinement relationship to one another, those two kinds of partitions will have phi of p and phi of q close to each other. So this is a much weaker property to state, and that means that it will be easier to prove in examples, and that means that it will be harder to prove that it has consequences. But that's okay, because we only have one proof of consequences, and we have lots of proofs that this is actually true. So, so this is sort of the right way about it. So that's the definition of the Cauchy criterion for partitions. Now, what are we going to do with it? Well, what do we do with this? What do we do with the Cauchy criterion for sequences? There are some sequences for which it is very, very hard to prove convergence, but it's easy to show that they're Cauchy. In particular, if you're dealing with series, this happens a lot. So what we do with this Cauchy criterion for sequences is we prove a general statement that says, and it's not easy, we prove a general statement that says if a sequence is Cauchy, then it's convergent. And we get the reverse too, but that's easy. And then instead of proving that things converge, well, we prove that they're Cauchy because it's easier. So that's our sort of two-step process to proving that things converge. First, we prove that anything Cauchy converges, and we only have to do that work once. And then when it's time to prove that something converges, we prove that it's Cauchy. Well, that's going to be the strategy here. We're going to have to show that a Cauchy function phi from partitions to a metric space, if it's Cauchy, then it converges. And then later, we'll prove convergence by proving Cauchy. So that's actually two statements. It's an if and only if. Convergent implies Cauchy and vice versa. Just like in the case of sequences, one of them is really easy, and really for the same reason. Honestly, this is all part of a slightly more general theory that well, I don't think it's productive in a complex analysis course to go into it too deeply. So it's all part of a more general theory. And we're just going to sort of see it happening twice, and you can imagine the generalization. So there are two statements that we need to prove in order to get moving here on Cauchy sequences. One of them is that if a sequence, not sequences, Cauchy versions of phi. If phi is convergent, then it's Cauchy. And second, if phi is Cauchy, then it converges. And the first is easy. So let's just call that a proposition. So if the limit as the norm goes to 0 of phi of p equals L, then phi is Cauchy. Notice it's phi that gets to be Cauchy, not p or q. So then phi is Cauchy. This is the easy version, and we'll prove this first, and it won't take long. So proof of this. So of course we'll assume that that limit exists. And I'm going to choose, well, I guess I'm going to let epsilon be greater than 0. So we'll let epsilon be greater than 0, and we'll choose a delta for epsilon in the definition of the limit. Not the definition of Cauchy, the definition of the limit. So in other words, we're choosing a delta so that we can be assured that for every, we're choosing a delta so that we can be assured that for every partition P, if its norm is less than delta, then indeed the distance from phi of P to L will be less than epsilon. And actually, choosing delta for epsilon will be nice, but choosing delta for epsilon over 2 will be even better. So I need to stop the timeout on the computer. So let's choose this for epsilon over 2, because that will be even better. Then what do we know? So then what are we trying to do? We're trying to show that we have Cauchy. So I'm actually going to continue and assume all of this. So let's let P and Q be partitions. And we're going to assume of them that the modulus of P is less than delta, and the modulus of Q is less than delta, and that P is refined by Q. In this proof, this doesn't actually figure in at all, which is suspicious. We don't even need this here, but that's okay. I'm trying to be faithful to the structure of this proof here. So now I have to show this. So then the distance from phi of P to phi of Q is going to be, well, triangle inequality. Phi of P to L, and then L to phi of Q. And that's epsilon over 2. That's less than epsilon over 2 plus epsilon over 2, which is epsilon. And so this establishes that the sequence is Cauchy. This is exactly the same proof we give for sequences. In fact, I keep saying sequence, but I should say this: the function phi is Cauchy. So notice we really did start with choosing epsilon, consistent with this. We really did next choose a delta, not for epsilon, but for epsilon over 2 in the other sequence, in the other definition of the limit. Then we picked out 2 things. We assumed the right things about them, and we proved that the distance between them was less than epsilon. So that really is a faithful proof that this thing is Cauchy. So that was pretty easy. The hard part is proving that a Cauchy phi actually is a convergent phi. So let's do that next. As usual, the hard part is we don't know what it converges to. If it's Cauchy, we're not given an L. And without an L, it's very hard to prove that something converges. So the first thing we have to do is to try to figure out what it converges to. I suppose the first thing we need to do is we need to state this thing carefully. So I think this one is hard enough. We should call it a theorem. So let's state this carefully. Let phi map partitions of A, B into X. And here, X needs to be a metric space. But honestly, we're talking about a condition that says that Cauchy sequences should converge. So it won't shock you that we need to assume that X is complete. So X is a complete metric space, which simply means that ordinary sequences on X, which are Cauchy, also converge in X. So X is a complete metric space. If phi is Cauchy, then the limit of phi of P as partition norm goes to 0 exists. All right, so that's the theorem you expected, the theorem I advertised. Let's talk about how we prove this. Well, the hardest part is getting started. We don't know, like, in order to prove that it converges, we need to prove that it converges to L. We don't know what L should be. And so the first thing we need to do is figure out what it's going to converge to, and then show it that it converges to that. So let's, first of all, we're going to choose a sequence of partitions. So P1 refined by P2, refined by P3, and we're going to continue refining these things, etc., so that the limit of the norms of these partitions as pi, as I goes to infinity, is actually equal to 0. Now, on what basis are we going to make these choices? Well, I'm just going to construct how we do this. I'm just going to illustrate how we do this. So, and it's simple, but it needs to be done. So, we have an interval from A to B. P1 can simply be these 2 points, right? So P1 is going to be A and B. So these are the only points that will be needed. And then P2 can be A and A plus, and the average. So A plus B over 2 and B. So then we can put in an extra thing, cut it in half. And then P3 can be A and the weighted average 3A plus B over 4, and the average A plus B over 2, and the weighted average A plus 3B over 4, and B. And I'm making it like giving complicated algebra for this, but I'm just adding 2 more points there and cutting it in half again. So here, what I've got is a picture of P3. So, and then P4 is going to have these extra divisions. And the reason I'm working here by like subdivision is because I want these to all be refinements of one another. I want them to satisfy this equation. And so basically cut in half every time, add a bunch more points every time, and then obviously with a construction like this, the norm will be cut in half every time as well. And so the norm will go to 0 as the index I goes to infinity. So this gives us a sequence of partitions which are all refine each other, and the norm goes to 0. What's that for? Well, the point of that is you can use that to construct a Cauchy sequence, an actual sequence, which is Cauchy. So let's let S sub I be phi of pi here. So if we let S of I be phi of pi, then so Si is in X, and the norm goes to 0, and so because the original partition function is Cauchy, because phi itself is Cauchy, then this thing will be Cauchy. So Si is a Cauchy sequence in X. And so who cares that Si is a Cauchy sequence in X? Well, X is assumed to be a complete metric space, and so it converges. So we get to assume that we get to conclude that the limit of Si as I goes to infinity is equal to L for some L. All right, so that's pretty good. Now we have the L. Now we need to show that for partitions sufficiently fine, then phi of that will be within epsilon of L. So in other words, we need to show that the limit of phi of P is actually equal to L. So let's claim that the limit of phi of P as partition norm goes to 0 is equal to L. Now, we know that these things have a limit which is equal to L, but these are very, very few of the very rich complexity of all the partitions that could exist. And so we don't know that this is true generally for all partitions. Nevertheless, we're going to get started on this. So how do we prove that a limit is equal to L? We let epsilon be greater than 0. And then we're going to choose a delta. So what are we going to do? We're going to choose a delta for epsilon over 3 in the definition of Cauchy. So the only thing we know about the function, about the function phi, which takes partition inputs, is that it's Cauchy here. And so we get to apply this definition here. that means that the distance between phi of p and phi of q will always be less than epsilon over 3, but only if we have a refinement relationship between p and q. Now, if we take a very fine partition here, even if it's very fine, it might not be a refinement of one of these guys, and it might not have any of these guys as a refinement of that. And so getting that refinement relationship just right is a little bit tricky. So what we're going to need to do is we're going to need to think about how to get a sort of what we'll call a co-refinement. So we're going to choose delta for epsilon over 3 in the definition of the Coachee, and then we're going to optimistically pick out just any partition, but I think I want to call it Q, that is delta phi. So let Q be a partition, and we're going to assume that its norm is less than delta. Okay, what we don't know is that Q has any refinement relationship to any of these PIs that we constructed, because these could be made out of any arbitrary irrational even lengths, whereas these are made out of these dyadic lengths. So we don't know any refinement relationship between P and Q. But we do know that there is some Q along this list that also has a norm less than delta. So I'm going to choose one of them. I don't know which one. So I mean, it doesn't matter which one. So let's let Pn, well, actually, this is going to be sort of choose Pn. So above, we're going to choose a very large number n, so that Pn will be nice. And what are we going to get from Pn? We're going to choose Pn above so that its norm is also less than delta. Now, why? Well, I would like to compare, I would like to say, first of all, how? How do I know I can do that? Because the limit of those is equal to 0, so one of them is going to be very, very small, okay? So that's how I know I can do that. Why am I going to do that? Because I know that Pn, having its very large norm, will be close to L. I need to also choose n large enough so that this limit will be sufficiently close to L. So let's see, do I have? No, I need to do that. So let me say, and furthermore, that the distance between phi of pi and L will be less than epsilon over 3. So so the distance between phi of pi and L will be less than epsilon over 3. So I got two conditions here that oops, that should be a Pn. I got two conditions that I'm trying to simultaneously impose on this Pn. Let's talk about whether I can get both. So this condition will eventually be true of the phi of pi's, right? Because the limit of the SI's is L. I know that from the sequence logic that we started with. So these things will eventually get within epsilon over 3 of L, and then they will remain within epsilon over 3 of L. So if they are at that point, if they have norm less than delta at that point, great. And if not, we just read farther on until they do have a norm less than delta. So both of these things are true eventually, and so I can choose a little n for which they are both true. Okay, now I would love to compare phi of Pn to phi of Q directly, but it doesn't work because neither is a refinement of the other. And so I need to next get a refinement of both of them. So I need to choose a partition R so what do we get? We need to get Q is going to be refined by R, and Pn is also going to be refined by R. So R is going to refine them both. How do you do that? You just merge together all the endpoints available in either one, and you get a refinement of both of them. And now, so the idea here is that phi, so just as an aside here, the idea is that phi of Q is approximately equal to phi of R, which is approximately equal to phi of Pn which is approximately equal to L. And I just need to make that formal, and then this will work. So notice that Q and R are both have norm less than delta. And I've chosen delta for epsilon over 3 in the definition of Cauchy. And they satisfy that refinement relationship. And so that will get me this distance less than epsilon over 3. So let's make that happen. So the distance between phi of q and L is going to be less than or equal to, and now we're going to do the obvious triangle inequality for this. That's going to be the distance between phi of q and phi of r plus the distance between phi of r and phi of pn plus the distance between phi of pn and L. So that's the triangle inequality that expresses what I mean by all these approximations. Now, Q and R are both delta fine. I know that Q is delta fine. The norm, in other words, the norm of Q is less than D. And R is a refinement of it, so its norm can't be any larger. And so we get R is also delta fine, and they are chosen for epsilon over 3 in the definition of Cauchy, and they have this refinement. So all of that means that this is less than epsilon over 3. The same can be said for R and Pn. Notice that Pn is chosen to be delta fine, and delta is for epsilon over 3 in the definition of Cauchy. So that's delta fine. R is a refinement of it. It also is delta fine, and they have that refinement relationship. And so by exactly the same logic, that gives us epsilon over 3 here. And then this thing is chosen in this way to be less than epsilon over 3. And that gives us, finally, epsilon. So what is that? That's the distance from phi of q to L being less than epsilon. That's for any q, a partition with norm less than delta. So that completes the proof that if thus phi converges, but technically I haven't defined converges. So let me say it out straight up this way. So the limit as the norm of p approaches 0, phi of p is equal to L as desired. And this establishes the important relationship between Cauchy, I want to say sequences, Cauchy functions phi defined on partitions, and convergent functions phi defined on sequences. And it will give us the permission later that whenever we want to show that one of these limits exists, then it will be enough for us to show that it's Cauchy. Why will we want to show that these limits exist? There's really only one main reason why we want to do this. This limit, the form of this limit, matches our definition of the integral. We'll want to show under certain conditions that the integral exists, that limit actually is defined and equals to something. And it's hard. So we're going to, instead of showing directly that thing converges to a certain value and predicting what the value is, we will show that function is Cauchy and then use this criterion.